Okay, today we will take up the study of different types of motors. In the last two lectures, we gave an overview of the special electromechanical systems, and we had a quick browsing of different machines which are in use, in operation in different segments like domestic, commercial, industrial and other areas of activity in engineering. And today we will start learning about single phase induction motors, because these are the ones which are used in large numbers. Maybe this almost is the bulk of the special machine category. Okay. And they are nothing but 3-phase induction motors in principle, but with some variations as it contains only limited less windings than the 3-phase, and also they operate with single phase. The single phase induction motors are so called because they operate with single phase supply, not that they have single phase windings per se. Okay. Now, before we actually go into the theory of it, I thought we can see what it contains or how is it made. Okay. So, I have here a single phase induction motor, okay, and it has a name plate here. You see, every machine has a name plate which specifies, it gives the specification of the motor. This is written as a single phase motor capacitor start. That means there is a capacitor which is only used for starting the motor, okay, which is connected in its auxiliary winding. Okay. Then it operates under 220 volts or 210 volts. Okay. It carries a current of around how much 3.1 amperes, okay, and it is a 0.5 HP. So, 0.5 HP will be 1 HP is how many watts? 746. So, it is around 375 watts. Okay. And obviously, 220 volts and 3.1 amps means it is drawing 600 VA. So, it is a poor power factor per se, and it operates at 50 hertz, it is written here, and it runs at 1420 RPM, and it is a 4-pole wound machine with a synchronous speed of 1500 RPM. That means it will operate at a slip of 80 RPM, right. It is 1420 RPM, and it is a continuous rating, and it operates at, it can operate about 40 degrees centigrade. Okay. And of course, some machine number is there and its manufacturer's details are there. So, this gives you the sort of a name plate or a horoscope of the machine, what it contains, okay, or what are the ratings. We know 220 volts, 50 hertz, say 3 amps and 1420 RPM. Okay. Now, let us see, let us open it, strip it and see what it contains. Okay. Now, I think these are the end plates. I think I need somebody's help, Puran. Okay. And so, these are the end sort of plates, you can say. Okay. And then we open the end covers, okay, on both sides. So, these are the, you see, both sides are the end plates, okay, right. I hope you can see this, the end plates. If you open the end plates, you will see here, this is the centrifugal switch. Okay. So, as the machine runs above certain speed, it will disconnect the capacitor. So, this operates by the principle of centrifugal operation. So, it will at high speeds it will disconnect, it is connected to a capacitor circuit. So, this is quite commonly used in most of the single phase motor where you have to switch. So, this is called the centrifugal switch here. Okay. Now, that will be connected to the shaft, okay. It runs with the rotation. Okay. So, we have seen now the end plates, okay, and we have seen these end covers. Okay. It looks simple, and of course, there are holes. Why there are holes here? For air circulations. Okay. Right. Now, what you have here remaining is inside part of the machine, okay, and which will obviously be a stator and a rotor, and this is the frame. What outside is the frame which is fixed to the base plates. Okay. It has to be fixed, you have some base plates. So, you put some nuts and bolts so that it does not move, okay, the stator, and inside the frame is you have the stator inside the frame. Okay. Now, let us see if you can right, I remove the rotor now. Okay. This is the rotor, and of course, the centrifugal switches, the switches will come on this one. Okay. I hope you can see this. You can see this rotor. What is the type of rotor is this? What is the type of rotor? So, it is a squirrel cage rotor. Okay, you do not see any squirrel here. Okay. So, it is a squirrel cage rotor, but only thing is there are bars. Okay. You will see actually these are the end rings. This is one end ring and other side is another end ring. Okay. So, this end ring is connected to the bars. You do not see the bars are embedded inside. This is almost like a closed slot, right. So, it is machined. So, outside you do not see any slots, but they are inside. Okay. So, they are pressed, there are the end rings, and there are squirrel cage, the bars are all inside. Okay. And this is a closed slot. So, bars goes inside the slots. Is it clear? It is not open slots. So, you have got a smooth surface on the rotor. Rotor is the outer surface of this, which is smooth, and this is laminated rotor. Okay. And then you see here on this side, what do you see here? What are these? These are the fans, because for cooling purposes this fan is also. So, this is like a totally enclosed fan cooled construction. So, fan is embedded, this is aluminum, it is like a mould the cast one. So, it is a die cast rotor, okay, and this is also connected to the shaft. So, you see the shaft, okay, which is driven through the rotor. This is the shaft, and there is a keyhole here. Why the keyhole is here? Yeah, coupling. You want to couple with another load. So, this will be helpful in that purpose. Okay. So, you see, I hope you have a fair about the construction. What is the rotor of a single phase induction motor? In fact, this same thing can be used for 3 phase also. And the squirrel cage has the phenomena. It can react to any number of poles, right? Is it clear about the construction of this squirrel cage rotor? Okay. And of course, here we have this. This can come here. The centrifugal switches, etc. Okay. Now, let us look at the stator now. So, if you is it clear? I think you can see it here. Okay. So, what you have, these are all laminations. You see, okay. In fact, these are coming out. Okay. These are the laminations. They are laminated, and these are the slots. Okay. You saw all these are slots, and between the 2 slots you have the teeth. Okay, they call it as teeth. So, right. So, uniform slots and uniform teeth. Okay. And what type of slots? If you look at the slots, they are all parallel slots, but round at the bottom, round bottoms. slots and there are wedges here, and so the conductors will be pushed inside here, coils are placed inside these slots. So, invariably there are two phases, 4 pole, okay, because you have a starting winding and a running winding, okay, in the main and auxiliary winding. So, you how many coils you need to have? You need to have 2 coils or 2 windings, okay, and 2 windings 4 pole, right. So, a coil, each of the coil must have a pitch of how many degrees? 90 degrees, right. So, if there is one coil side here, another coil side come exactly 90 degrees here. So, a coil may be spanning like this, not like this, it does not span like this, it becomes a 2 pole if you span from here to here, because it will span from here to the 90 degrees mechanically, okay. So, that is how you will have. So, you will have, so if there is one coil you place here, then next coil should be placed 90 degrees from the, if the main winding is axis is here, auxiliary winding axis must be 90 degrees electrical, which may be 45 degrees mechanical. Is it clear? 45 degrees mechanical. So, you have 4 pole windings. So, you need to have a understanding of this. So, I hope you have a clear picture of what is the stator like of a single phase motor. Okay. This will be slightly different than the it will look, you may even have a 3 phase winding on the same slots, okay, or you can have single phase winding. So, single phase, so you put 2 windings at 90 electrical degrees in these ones, okay. So, that is the configuration. So, this way I hope you have a clear picture of the construction of single phase induction motor, which comprises what? End plates, end covers, centrifugal switch if it is whenever required, a squirrel cage rotor, then you have the stator, the frame, the base plates, okay, which is attached to the frame, and the stampings and the core, because windings are not shown here, you can put the windings and make a machine out of it. Okay. Now, there is these frames are also classified as some numbers, right. There is a frame number 112 frame, 132 frame. Do you know what does it mean? Huh? Size of the frame, no. What do you mean? No, I say 112 frame, 90 frame. Just like shoes, you know, you have 7 number, 8 number shoes, etc. There is something connected with it. Yeah. So, the thing is, if I put it, if you put a center, if you have a center of the shaft here, if the center of the shaft is here, then from there to the base plate, that is the in millimeters is the frame numbers. So, 112 means it is center of the shaft to the base is 112 millimeters. I mean, they are practical engineering facts you need to know, and invariably they are not so clearly available in formal literature, okay. They are engineering data, etc. Okay. So, now we will start our, we have seen the practical construction of the single phase motor. Because this is only one type, there could be other variants of the same thing, like ceiling fan. In ceiling fan, it is a single phase motor, single phase, and it also has 2 windings and a capacitor, but it is a permanent capacitor. You do not have a centrifugal switch there, because a fan runs at different speeds, okay. But the ceiling fan, the one difference is the rotating part is outside, right. So, that is, so it is an inverted one. So, your squirrel cage is outside, that is the ceiling fan. Or a table fan, you instead of a this wound stator, you have a shaded pole. So, second winding is just a closed ring, that is called shaded pole one. So, the different variants are there of these motors. Okay. Okay, now we will go to the okay. Is it coming now? Right. So, we will start our the concepts now. Single phase and two phase motors. We have seen there are two windings, rotor, squirrel cage and everything. Okay. Now, before I go into the single phase motor, I thought last time we went a little fast on some of review of the other motors. We will have a recap of the other machines, a classification of motors, so that we can have a holistic view of things. Okay. One we studied, we didn't study, but we just mentioned about the permanent magnet commutator motors. So, these were the DC motors where the field winding is replaced by the permanent magnet. Okay. So, it has a high torque compared to wound field motors, because why it has a high torque? Because it can take up more flux, okay, and it has a high power to weight ratio. When high power to weight ratio is an important thing for any machine, a quality factor is the power to weight ratio. Okay. And so, permanent magnet commutator motors can give you more power because it can produce more flux. Okay. Then there is a brushless machine, which is a rotating machine where it is an inverted one. You put the magnet on the rotor, okay, and you put a 3-phase winding on the stator, okay, and you switch the windings. Okay. So, it has a high nominal torque range, okay, and it has a better performance compared to commutator motors, because the problem of commutators are not there, okay, and the switching arrangement. Okay. Then we also discussed about the printed circuit motors. They are also permanent magnet motors. Okay. They are also permanent magnet. These are the permanent magnet, but you have the armature here. So, they have axial flux and radial currents mounted on a shaft along with the. Now, you have a commutator here. So, this is a commutator type of printed circuit machines, which are also made on the DC side. Okay. This is a disc motor printed circuit. It is a, of course, complex structure, low inertia, low torque ripples, and not very high efficiency and small size. Okay. Then these permanent magnet motors are used in electronic computers, computer drives, automobiles, domestic appliances like vacuum cleaners, and battery driven electric vehicles. So, that is, these are the rated considered to be the applications of permanent magnet DC motors. Why they called DC? Because they normally operate with DC supply. Okay. The commutator motors are brushless DC motors, your normal supply is DC. Okay. Then you can have a permanent magnet synchronous motors, where it is a normal synchronous motor, which is a wound field on the rotor, you put permanent magnets. Okay. So, this is like a induction motor, but magnetic field is produced by the permanent magnet. Okay. Okay. Now, stator of course is 3-phase stator, and rotor you have a surface mounted permanent magnet. Okay. Then it has high reliability and efficiency, low electromagnetic interference, sensorless speed control is possible, and suitable for position controls. Synchronous motors you can do a position control for this. Okay. And again they are used for automotive applications, refrigeration, servo drives, power steering, etc. Okay. Then we also reluctance motors. This was another motor which we mentioned, and it can be a split phase induction motor with salient pole on the rotor, that can also be possible. So, it is a variable reluctance motor, it is not a switched reluctance, this is a conventional reluctance motor, and rotor reluctance motor same as we have a some slots or some tooth being removed. So, you make a uneven reluctance in that way. So, starting is you can start it as an induction motor and run it as a synchronous machine. Okay. So, these reluctance motors earlier they were used for clocks etc., highly precise speed, low power factor, efficient in low power range, and they were used in timing devices or clocks earlier, and phonograph turntables, signaling devices and recording instruments. So, but nowadays they are also being replaced, okay, but they are still used because of simplicity of the reluctance machines. Okay. Then other one we mentioned about hysteresis motor, where stator is similar to a single phase motor. The one thing is you can have a stator could be same, rotor can be squirrel cage, or rotor can be a variable reluctance, it becomes a reluctance motor, or rotor can be hysteresis. That means you make a iron rotor with a material with large hysteresis loop. So, it will be able to store magnetic energy, okay, and retain magnetic energy. So, it also like an induced permanent magnet is being created there. Okay. So, then if the rotor is a permanent magnet and stator is a rotating field, it will become a synchronous motor. See, I hope you know what is meant by synchronous or asynchronous. Synchronous motor means it will catch up with the speed of the inducing field, whereas in the induction motor it will slip from the air gap field. That is the main difference. Okay. One slips, so it does not slip. Okay. Now, whereas reluctance motor does not slip, hysteresis motor does not slip. So, they form a category of synchronous motors, okay, whereas the construction wise it may be similar as the stator is concerned. Okay. So, rotor is a material, okay, having high retentivity, okay, and permeability. Okay. So, it has no mechanical or magnetic vibrations because rotor is a solid rotor, uniform torque in complete speed range, okay, it is quiet and smooth operation, and it is used for high inertia loads, precision audio equipment and military and space applications. They are quite used wherever you require a constant speed, and cost is not a consideration. And we also discussed about stepper motor is a brushless, variable steps are there. So, by controlling by putting exciting different windings like let us say A, B, C, D. So, you can create the magnetic field centered around different axes. So, rotor will catch up with that axis. So, it will rotate, okay, in steps. Rotor can be turned to a precision angle. You do not have to rotate continuously. If you want to lock in say at 20 degrees, 40 degrees. So, you can design the geometry of stator and rotor slots in such a way that at each of the step change the field is locked at certain positions in the air gap. Okay. So, rotor gets locked into that inducing field. Okay. So, it is a doubly salient machine, you can have saliency here also. Okay. So, you can see here there is a toothed rotor and toothed stator, there are tooth in the saliency on both stator and rotor. So, this is the stepper motor. Okay. So, they have a low cost solution for position control, okay, and it is inherent zero following error in servo systems because it follows very systematically, it does not slip from, if you give a command it will go to that position. Okay. Tight open loop speed control is possible and it has a good holding torque. Okay. So, it is used for cruise control, automotive gauges, computer drives and printers, medical and scientific instruments. Okay. And the other type is not a reluctance motor, called a switch reluctance motor. Okay. So, you make a variable reluctance rotor, but stator is like a stepper motor stator. Okay. So, you have several coils, you switch one at a time. Okay. So, when you switch a particular coil, the rotor will align based on the principle of minimum reluctance. Okay. So, just like what is the, why does a iron bar aligns with the horseshoe magnet, because it will align in such a path of minimum reluctance, right. So, okay. So, SR motor is a rotating machine where they are doubly salient. Okay. So, they have, stator has set of coils wound on one pole, okay. Rotor has number of phases. Okay. So, by combination of stator rotor poles, you can have different combinations. Now, this is one machine where stator and rotor poles are not necessarily same, invariably they are not same. Okay. Whereas, all other machines, stator rotor poles must be same. Like a synchronous machine or induction machine or DC machine, stator poles must be same as rotor poles, whereas in switched reluctance machines they are invariably different. Stator poles are not the same as stator poles. Okay. So, they are used, their features are lowest constructional complexity, because the rotor is just a solid one, no windings on the rotor. Okay. So, the losses are less, there are no rotor losses, unlike in a induction machines. Okay. And you can have a sensorless speed control, high speed operation, you can run at very high speed, because all you need is to switch at very high speeds on the stator coils. Okay. And you can have a high startup torque, you can start with high torque. Okay. And they are used in centrifuges, washing machines, small appliances, fans, and several applications have been there. Right. If you look at the write up of Peter Lawrenson, who was one of the inventors, many applications have been listed for this. When we go to switched reluctance motors, maybe we will go into more details. This is just a review of this thing. Construction wise, we have seen this. This is, what is it, this machine? This is a single phase induction motor. Stator wound, we have seen how they are winding on this, and there is a squirrel cage. Okay. This is SRM. There are several coils are there here. Okay. And then you have the rotor is variable reluctance, right, and this is a smooth cylindrical rotor, this is a variable reluctance rotor, no windings here. So, as you excite different coils, and this will align with the appropriate coils. So, this is a SRM motor. So, this is induction motor, single phase induction motor. Okay. This is the switched reluctance motor. Okay. This is stator and rotor. And of course, then we also talked about linear motors, like a disc motors, which are having a slight variation than conventional motors. Linear motors also have a variation where you spread it out. Okay. This is unrolled. So, producing a torque, it produces a force, and instead of producing a rotary speed, it produces a linear speed, okay, along the length, right. So, it has a, this we have already discussed it earlier. Now, they are highly controllable acceleration, it can be very high speed and controlled acceleration. High power can be converted into linear motion, because all you need is high magnets. In fact, one of the concepts which have been exploited is superconductors. You can also have a cryogenic coils, okay, superconductors. So, very high currents can be there. Okay. Superconducting magnets can carry, you do not need any core at all. All you can, if superconductors can carry very large currents, it will produce large fields, large flux, etc. Okay. and they are used in magnetical levitated trains, maglevs, lifting mechanism, hypervelocity weapons and spacecraft propulsion, etc. Okay. Now, this since so we have a idea of what are these category of special machines now, okay, and what are the different features, the power ratings, speed ranges and so on. Okay. So, today we will go back to learning the fundamentals of the single phase induction motor. Of course, this is a variant of the 3 phase motor. What is a 3 phase motor? You have 3 phase motors which is generally used in most of the industries, 3 phase motors. They have 3 phase windings in the stator, okay, and rotor is squirrel cage or wound rotor. Okay. There are slip ring rotors also in 3 phase, but seldom in single phase. Single phase all are squirrel cage because they are low power. Okay. They are all fractional kilowatt or fractional horsepower motors. Okay. Right. And in a 3 phase machine, rotor is squirrel cage, aluminum bars, okay, is called a die cast end rings. So, one is a die cast one, another is the wound rotor. Wound rotor will have 3 windings as in the stator. Okay. Now, 3 phase motors features are high reliability, this is one of the, okay, and reasonably good efficiency, they are gone even up to 94-95% efficiency, very high starting torque and no electromagnetic interference and low cost per horsepower. These are the cheapest machines made, 3 phase machines. Okay. So, they are used in all types of applications, electric drives, compressors, air conditioners, pumps, washing machines, fans and so on. Okay. Okay. Now, single phase machines, where are they used? They are used for near constant speed applications. They are rarely used for variable speed. Single phase machines, except for some limited speed range like fans, etc. Okay. So, they are used with single phase supply. Okay. So, they normally have 2 windings in the stator, main and auxiliary winding, and the rotor is squirrel cage. Okay. Again I am repeating the statements so that it drives home the point. Okay. And 2 windings in the stator are categorized as follows. Okay. There is what is known as a split phase, where 2 windings are having different impedances, they are not symmetrical, okay, and they are invariably wound at 90 degrees, but one will have a higher resistance and lower reactance. Okay. Another is capacitor start, the one which we had seen. Capacitor start means the centrifugal switch will disconnect the capacitor after it reaches certain speed. Another is capacitor run, like a ceiling fan. Ceiling fan, no disconnection of capacitor is permanent. So, auxiliary winding, main windings are there all the time, and there is one capacitor start, capacitor run, means you can have 2 capacitors, one to start, another to run. So, a centrifugal switch should operate, should disconnect the starting capacitor and connect the running capacitor after a certain speed. Okay. Now, supplying both main and auxiliary winding enables the single phase machine to be driven as a 2 phase machine. Okay. Now, supposing you have 2 windings, you can also have a 2 phase supply. So, you can run just like 3 phase machine runs on 3 phase supply, a 2 phase machine can also run on 2 phase supplies, but for that you need a 2 phase supply system. Okay. Now, the reliability, single phase motor highly reliable and complex sensorless speed control. Okay. It is not so easy. It has a low EMI, electromagnetic interference, and it can be directly driven online. See, single phase motor is one of the motor where you do not need a controller per se, you can just directly switch it onto the supply. There are very few machines which can directly switch on to supply. 3-phase induction motor, single phase induction motor, a DC motor, to some extent synchronous motor. Whereas stepper motor, switched reluctance motor, they need controllers. Without controller, they just are a dead machines. They just cannot operate without a controller. Okay. Because single phase motors have very wide applications, domestic applications, kitchen applications, fans, industrial machines and so on. I think it is okay. So, there are umpteen number of applications where single phase machines are used, and since they are produced in millions, every house may have 10 single phase induction motor. You find them in refrigerators, you find them in air conditioner, you find them in desert coolers, you find them in even winter you have these heaters, okay, blowers, the exhaust fans, tailoring machines, okay, and so you have them in all places, okay, found in variety of applications in household to industry. Okay. So, these are single phase unbalanced machines, is not it? They are not balanced machines, because two windings are not similar, though they may be invariably at 90 degrees. So, what we are now looking at is a machine which is simple to make, but complicated to understand, right, and how it works. Okay. There has been several papers in the early last century, maybe mid last, I mean 30 to 50 or something, where people have been debating about its whole working. Okay. Now, so we had to see a qualitatively how it works first, and then we had to see its performance for various connections, and we also look at what is the concept called rotating field theory and unsymmetrical operations in this lecture. Okay. Okay, I mean again we are repeating the statements here. The construction we have said single phase motor is like a polyphase squirrel cage motor, only difference is stator winding is different. What is the difference between single phase and 3-phase machines? Rotor is same, stator is different. Okay. And they normally do not start, they are not self starting, there is a problem of starting. Okay. Unlike in a 3-phase machine can start on its own. Okay. So, here it will be the problem of starting. Okay. And we consider what is known as the forward and backward fields here. Okay. Now, let us the conceptual what we have seen earlier, you can write it schematically like this. So, you have a voltage source, single phase voltage source. So, you have it has a fixed voltage and fixed frequency, right, and it will pass a current into the windings. This will be AC, right, and rotor is squirrel cage rotor. Okay. And this is the stator winding. Okay. I am taking only one winding. Okay. Let us look at the second winding later. Okay. Okay. Now, if you pass a current through that winding, what will happen? It will produce air gap MMF, right. What will be the nature of air gap MMF? It will be a function of position, space, and it will be a function of time. Okay. So, if you have one winding and pass a AC current, the field that is produced will be different at different positions and different at different times. How will? So, this is the formula, okay. Cos theta, cos omega t. Theta is the electrical angle, omega is the electrical radians per second, the supply. Okay. So, what what we are trying to say is, if I put a coil and pass a current I, because the rotor is squirrel cage, this is the air gap, is not it? Where will my magnetic field be centered now? Which will be the axis of the magnetic field when you pass a current through that? Where will it be? Where do I get the maximum MMF? MMF will be radial, I hope, is not it? MMF will be radial. Where, at which point, after all this is, there are different points in the air gap, is not it? There are different points in the stator surface. This is stator surface, okay. This is the stator surface and this is the air gap. Tell me where do I get the maximum air gap MMF? Which position? 90 degrees from the, from where? So, let us say this is A dash. It is the axis of the coil, okay. It is axis of the coil, let us say A coil, let us say, I am just putting, right, and it is here you find, it is here you have the maximum MMF. Isn't it? Okay. And what about here? Why are you partial? So, this will be minus F max. If this is plus F max, this is minus F max, right. So, that is the center of the coil where at this radial point the maximum MMF will be there, okay. Now, this I, how does it vary with time? Let us say I varies this is I. So, you can say I varies as I max cos omega t, omega is electrical angle. So, from this position I measure theta E, okay, any position theta E, theta electrical from this. So, here theta is 0 and here theta is how much? 180 degrees, 180 degrees electrical, agreed. Now, this current is varying in time. Now, at this position, say this is omega t is 0 and this is at how much? Pi, sorry, this is pi, pi by 2, 3 pi by 2, 2 pi, isn't it? What will happen at 0 instant of time? Where will my magnetic field be? It will be centered around this, okay. And is it clear? At theta, at omega t is 0, so F max is at theta equal to 0. See, F is F max, is it corresponding to I max? Here this is I max. current is I max, maximum current is flowing in the winding at that instance of time. Therefore, magnetic field is standing there as if I kept a magnet here, I have kept a magnet here, like this is north pole, south pole, right. So, the flux will be the normal flux lines. So, flux lines will be right, flux lines will be going like this. So, which stator is at higher potential or the rotor is higher potential, and where? Okay. So, at this point this is at higher potential than this, is not it, because only then the flux can go from rotor to stator surface at this point, So, at this whole area, stator surface is at a lower potential than the rotor surface. Is it clear? So, from here to here, okay, and whereas say from here to here, what is happening? Stator surface is at a higher potential compared to the rotor surface magnetically. So, that is what we call it a magnetomotive force or MMF. So, here, so this will be a plus, if you say this is 0, and this will be the minus from that point of view. So, it all depends on what you define as your MMF. Okay. If you MMF you define as the potential of the stator surface with respect to rotor surface, then here it will be negative, here it will be positive, while the flux is entering the stator surface. So, obviously, you have created a south pole here and a north pole here on the stator surface at that instant of time. At this instant of time where current is I max, you have created a north pole, south pole on the top and a north pole at the bottom at the stator surface. In other words, a rotor surface is the other way around. Okay. Now, what will happen at omega t equal to pi by 2? Yeah, just one second. Omega t equal to pi by 2, what will happen? What will happen? What will be the field? 0. So, the there is no magnet at all, it is dead. Stator surface is same as rotor surface, and at pi it will be opposite, okay. And here, so here is 0 and omega is equal to pi by pi, it is equal to minus f, and the same thing repeats here, okay. Again here 0 and here it maximum. So, what you have got is a magnet placed here at this point, whose strength is go on changing with time. At one time the magnet has a 0 potential, other time magnet is a maximum potential, and other time it has a negative maximum potential. Okay. So, you have a what type of field you call it as? Is it a rotating field? So, it is a pulsating field. We get a pulsating field, okay. So, it will goes on changing with difference to time. So, you have omega t equal to 0, then you have this is the axis anyway, okay. This is with reference to theta electrical, okay. This is 0 minus this is let us say minus pi by 2 okay, right. So, and at omega t equal to 90 degrees it will be like this, and pi and then 3 pi by 2 and also at 2 pi. Is it clear? So, what we have is a pulsating field, but axis does not change, it is the same axis, is same, it is in the same axis. So, we get a pulsating field. So, we will stop here and next time we will see what do we understand out of this pulsating field and how do we use it for understanding the behavior of the motor. Okay, stop it here.